Hey guys, in this video I will present a solution to Serbia Math Olympiad 2016 problem 6. Firstly, we have a look at the statement. We consider integers a1, a2 up to a2 to the power of 2016 such that they lie between 1 and 2016 and such that a1 times a2 times up to times ak plus 1 is a perfect square for all possible indices k between 1 and 2 to the power of 2016. We wish to prove that there exists an index I such that ai is equal to 1. Firstly, we would like notation for solving the problem. So define pk to be the kth partial product of the ai, so pk is equal to a1 times a2 up to times ak. So the condition tells us that pk plus 1 is a square for all possible indices k. This problem appears to be suitable for a proof by contradiction. So assume that ai is greater than 1. When I was first confronted with this problem, I tried figuring out why it was problematic to have all ai's greater than 1 and still having this condition hold true. Because after all, we are trying to get a contradiction out of this. So I took a look on how the construction of an easy counterexample fails. Let's consider some integer p such that p plus 1 is x squared. Furthermore, we introduce an a, which should represent those ai's, and then a times p plus 1 is equal to y squared. Now, we would like to have an easy counterexample. Of course, this is going to fail, otherwise this problem is not true. So in the easiest case, all of these ai are just some constant greater than 1. So let's continue this to get to the point that a squared times p plus 1 should be z squared. The first and third equation should make you kind of suspicious, because of course p represents an integer that is much larger than the integer a represents. Because since the ai are at least 2, we can get that pi is greater than or equal to 2 to the power of i. For I going up to 2 to the power of 2016, this is of course going to grow much larger than 2016. Therefore, we get that a squared times p plus 1, which is nothing but a squared x squared minus a squared plus 1, and this also equals to z squared. Of course, that term is strictly less than ax squared, at least for a greater than 1, but this is greater than a squared x squared minus 2ax plus 1, at least for a less than 2x, and this is an interesting bound because it equals ax minus 1 all squared. And of course, because we are dealing with integers, this is a contradiction. We want to use this contradiction right here to get a contradiction in our main proof. Therefore, we would like to have large pk pl such that pk divided by pl is a square. And in this case, clearly pk must be greater than pl. And if this fraction is not really large in comparison to pk and pl, we can lead this to a contradiction using what we have found right here. A positive integer n is a square if and only if for all q primes mu q of n, which is the number of times q divides n, is congruent to 0 mod 2. This is a useful characterization for square numbers in our case, because we know that the pk can't have many different prime factors. In particular, if we let m be the number of primes less than 2016 and q1 less than q2 less than qm first m primes, then we know that all of the pk are only divisible by those m primes. So we get that pk equals to q1 x1k times q2 x2k up to qn to the power of xnk. And by this we can define a tuple for each of the tk, which I define to be t of pk. And this shall be the tuple of those numbers x1k, x2k, all the way up to xnk in f2 to the power of m. So this is an m tuple where the ith entry is 0 if xik is divisible by 2 and 1 otherwise. We note that there are only 2 to the power of m such tuples, which is kind of small in comparison to 2 to the power of 2016. This is very useful because now we know that among any 2 to the power of m plus 1 partial products we can find pk greater than pl such that t of pk equals to t of pl, which of course implies that pk divided by pl is a square. Recall that originally we were interested in large pk and pl such that their quotient is a square. So the most useful conclusion that we can get out of here is that among the indices between 2 to the power of 2016 minus 2m and 2 to the power of 2016, those are the 2 to the power of m plus first largest possible indices. We can find an L less than k such that pk divided by pl is a square. We note that in the environment of our first observation, pk divided by pl plays the role of a squared. So we would like to bound this from above. We get that pk divided by pl is by definition al plus 1 times al plus 2 all the way up to ak. We are dealing with k minus l terms, each of which are at most 2016. Therefore, this is less than or equal to 2016 to the power of k minus l. And by definition of this interval, we get that this is at most 2016 to the power of 2 to the power of m. We would like this inequality to be true in our more global environment to get a contradiction here. We already know how to bound our value of a squared, so let's take a look at x squared. X squared is equal to p plus 1, and now in our new environment p is represented by pl. So this is pl plus 1, and we want to bound this from below. Clearly this is greater than pl. We already have a tool for bounding pl from below, mainly that pi is greater than or equal to 2 to the power of I. Furthermore, we know that L is greater than or equal to 2 to the power of 2016 minus 2 to the power of m. Now m, the number of primes, at most 2016, is clearly less than or equal to 2015. Therefore, this can be bound from below by 2 to the power of 2015. Therefore, PL is, by our above inequality, at least 2 to the power of 2 to the power of 2015. We see that we have exponents 2 to the power of 2015 and 2 to the power of m. Furthermore, 2015 is quite a bit larger than m. For our purposes, we are going to need the bound m is less than or equal to 2011, which is clear from the fact that we can find 5 non-prime numbers less than 2016. Therefore, this quantity is at least 2 to the power of 4 plus m, which we can write as 16 times 2 to the power of m. This equals 2 to the power of 16 to the power of 2 to the power of m. And we see that 2 to the power of 16, which is larger than 2 to the power of 11, which is 2048, for instance. This is, in any case, much larger than 2016 to the power of 2 to the n. This tells us that in our environment, x squared is greater than 2016 to the power of 2 to the power of n, which is greater than or equal to a squared. But we see that a squared less than x squared implies a less than 2x, which implies a contradiction. So also in our problem we get a contradiction from our assumption that ai is greater than 1, and therefore we have shown that there exists an index such that ai is equal to 1.